In this lesson we continue the analysis of the blood test dataset. A key finding from the previous exercises is that these data include many correlated variables, which should not be included to avoid the masking effect. Masking occurs when the inclusion of a regression variable hides the effect of other variables that are related to the included one. During the previous lesson we saw that the correlation matrix could fix this issue. But unfortunately correlation does not work in more difficult situations. Indeed, by definition, the correlation matrix gives information about pairwise interactions, but variables may interact in more complicated ways. For example, a variable can be obtained as the linear combination of two other variables. The problem is not trivial since dependencies between more than two variables are difficult to inspect. Therefore, variable selection methods become essential to select the best subset of regression variables. Among several possible approaches, we focus on the so-called Akaika Information Criterion (AIC). To perform model selection with the AIC, we must load the MAS library. Then, let's divide the available data into test and training set. Looking at the code, object data_training contains the first 300 observations, used to train the model. Regarding the test set, we define two objects. Object x_test contains the regression variables for the remaining 24 observations, columns from the second to the last one, while true labels are saved in vector y_test. The first step is to fit a model using all predictors. As we saw, this is done in R with the lm function, specifying urea as response variable and then using a dot after the tilde to state that. We use all available variables. We run the command and we save the output in an object called full_model. This is the starting point of the AIC, which starts from the full model and then iteratively removes variables until it can no longer improve the model by eliminating any other variable. These steps are automatically performed in R with the step AIC function of the MAS package we just loaded. To inspect the output, it is enough to print the resulting object named fit_AIC. In the end, the estimated model only contains 4 variables out of the original 10. Note that we specified the trace equals 0 option to suppress the output, but setting trace equals 1 you can inspect all the different models visited at each iteration. To compare the model selected by the AIC with the full model, we can compute the mean squared error on the test set, which is the sum of the squared differences between the predicted values and the real ones, averaged over patients in the test set. Being an error metric, lower values are to be preferred. We now move to a different problem, loading a modified version of the dataset named glucose levels txt. In this version of the dataset, the glucose level is not numerical but categorical, high, average or low. First, we load the data and produce a bar plot with the absolute frequencies of the labels. This is simply done using the plot function with the name of the desired variable as argument, after casting the variable of interest as a factor. We use the KNN in this case, loading class package as shown in the slide. As above, we divide the data into test and training set. First, we set the seed to ensure the reproducibility of the results. Then, model training and prediction of new labels is performed with a single command, that is KNN. The arguments are the predictors in the training set, the predictors in the test set and the labels in the training set. Moreover, the final argument, which is crucial one, is the number of nearest neighbors used to predict the labels of the new observations. Once obtained, the predicted labels are compared with the true ones using the table command. It produces the so-called confusion matrix whose values on the diagonal are the correct predictions. Namely, 13 out of 15 new patients with a medium level of glucose are correctly classified, while only 1 out of 6 patients with low level, and none of the 3 patients with high level. Thus, the overall accuracy is only the 58%. A simple way to improve our predictions is to fit the model with different values of k. We show in the figure the accuracy for values of k that range from 3 to 21. There is a huge improvement when increasing k from 3 to 5, but for higher values, the accuracy stabilizes on the same value. Therefore, we may conclude that k equals 5 is the best choice, as it reaches the highest accuracy without relying on a too complicated model.